This lecture is for the course MAT201 Partial Differential Equations and Complex Analysis. We'll look at what are partial differential equations and how to form a partial differential equation from a given relation. The prerequisites for this section are functions of two variables, partial differentiation, and the chain rule for evaluating partial derivatives. The references for this course are the books Higher Engineering Mathematics by B.S. Grewal and Advanced Engineering Mathematics by Peter V. O'Neill. Now, what is a partial differential equation? If you remember, an ordinary differential equation was an equation made of a function y of t or y of x and its derivatives. In the same way, a partial differential equation or PDE involves a multivariable function and its partial derivatives. For example, if z is a function of x and y, then x dou z by dou x plus y dou z by dou y equal to z is an example of a PDE. Dou square z by dou x dou y equal to dou z by dou x the whole cube is another example of a PDE. Now, just like for ordinary differential equations, partial differential equations also have order and degree. So, the order of a PDE is the order of the highest partial derivative in the equation. So, in the first example above, all the derivatives are of first order. So, this PDE has order 1. Now, the second example has a partial derivative of second order. So, this PDE has order 2. The degree of a PDE is the degree of the highest order partial derivative in the equation. In both of the above examples, the highest order partial derivatives have degree 1. So, both the PDEs have degree equal to 1. To make calculations easier, we'll introduce some notation as regards partial differential equations. We use z to denote z of xy, where z is a function of two independent variables x and y. We also use the following notations for the partial derivatives of z. Dou z by dou x is denoted by p and dou z by dou y by q. For the second order derivatives, dou square z by dou x square is denoted by r, dou square z by dou y square by t, and the mixed partial derivative dou square z by dou x dou y is denoted by s. How do we form a partial differential equation given a relation? So, we are given a relation f of x, y, z, a, b of the variables x, y, z, maybe some arbitrary constants a and b, and some arbitrary function f. And we want to find the partial differential equation satisfied by this relation. So, to form a PDE from a relation involving 3 or more variables, we can eliminate either the arbitrary constants in the relationship or eliminate the arbitrary functions in the relation. To form the PDE, we'll evaluate the partial derivatives of z with respect to x and y. Then see if we can write down an equation involving only z, x, y, and the partial derivatives. In cases where we cannot evaluate the partial derivatives of z directly, we'll evaluate the partial derivatives of some arbitrary function. But the problem we face is we don't know beforehand what is the order of the PDE satisfied by some general relation. This means we don't know what order partial derivatives to take to find the required PDE. Luckily, we have a rule of thumb to figure out what should be the order of a PDE or how many times we should differentiate. So if the number of arbitrary constants in the relation is equal to the number of independent variables, then the PDE formed is of first order. If the number of arbitrary constants is greater than the number of independent variables, then the PDE is of second or higher order. If the PDE is formed by eliminating arbitrary functions, then the order of the PDE is in general equal to the number of arbitrary functions which we are eliminating. What does this mean? We can use the number of arbitrary constants or arbitrary functions in the relation to find out how many times to differentiate. Let's look at some examples of eliminating arbitrary constants to find the PDE. Derive a PDE from the relation 2z equal to x square by a square plus y square by b square. This relation doesn't have any arbitrary functions, but we do have two arbitrary constants a and b. If we eliminate these constants, we will get the required PDE. Now there are two arbitrary constants a and b and two independent variables x and y. The number of constants equals the number of independent variables, so it is enough to evaluate the first order derivatives. Because by our rule of thumb, the PDE satisfied by this relation should be of first order. So find the first order partial derivatives of z. 2 times dou z by dou x equal to 2x by a square. 2 times dou z by dou y equal to 2y divided by b square. Again, using our notation from before, dou z by dou x is p, and that's equal to x by a square. Dou z by dou y or q equals y by b square. Then we can write 1 by a square equal to p by x and 1 by b square equal to q by y. Now we have the arbitrary constant in terms of just x, y and the partial derivatives. So we can substitute for both constants in the original equation and then we'll get the required PDE 2z equal to px plus qy. Let's look at another example of the same type. Find the differential equation satisfied by all planes which are at a fixed distance a from the origin. Any plane at distance a from the origin has an equation of the form Lx plus my plus nz equal to a, where L, m and n are the direction cosines of the normal from the origin to the plane. Now at first sight, there are three arbitrary constants in this relation, L, m and n. But remember, L, m and n in this case are the direction cosines. So they should satisfy L square plus m square plus n square equal to 1. That means we can write n as square root of 1 minus L square minus m square. So the equation of the plane can be rewritten as Lx plus my plus square root of 1 minus L square minus m square times z equal to a. Now this relation is with a fixed constant a, just the two arbitrary constants L and m, and two independent variables x and y. Since there are two arbitrary constants and two independent variables, the number of arbitrary constants equals the number of independent variables. So the PDE satisfied by this relation should be of first order. As before, we'll take the relation Lx plus my plus square root of 1 minus L square minus m square times z equal to a and differentiate it partially with respect to x and y. So differentiate with respect to x and we'll get L plus square root of 1 minus L square minus M square times P equal to 0. So L equal to minus square root of 1 minus L square minus M square times P. Again remember, P is dou Z by dou X. When we differentiate with respect to Y, we'll get M plus square root of 1 minus L square minus M square times Q equal to 0, which means M equals minus square root of 1 minus L square minus M square times Q. Now we have three equations. Let's eliminate L and M from these three equations. So take equations 2 and 3, square and add them. Then we get L square plus M square equal to 1 minus L square minus M square times P square plus Q square. If we expand the right hand side, this becomes P square plus Q square minus L square plus M square times P square plus Q square. We can solve for L square plus M square, and this is equal to P square plus Q square divided by 1 plus P square plus Q square. Now in the original relation, we had a term involving 1 minus L square minus M square. Let's evaluate that. 1 minus L square minus M square will be 1 minus P square plus Q square divided by 1 plus P square plus Q square, and that's equal to 1 by 1 plus P square plus Q square. Now substitute for this term in equations 2 and 3. So L will be minus P divided by square root of 1 plus P square plus Q square. M equals minus Q by square root of 1 plus P square plus Q square. Finally, we can substitute for L, M and square root of 1 minus L square minus M square in the original relation, equation 1. So that will give us minus Px divided by square root of 1 plus P square plus Q square minus Qy by square root of 1 plus P square plus Q square plus Z divided by square root of 1 plus P square plus Q square equal to A. Now it's just a matter of rearranging the terms in this equation and we'll get the PDE we want. Z equal to Px plus Qy plus A times square root of 1 plus P square plus Q square. This is the PDE satisfied by all planes at distance A from the origin. Now we'll look at examples where we eliminate arbitrary functions. Derive a PDE from Z equal to x plus y times phi of x square plus y square. In this question, we have an arbitrary function phi in the relation, but there are no arbitrary constants. So we have to eliminate the function phi to get the required PDE. Now there is only one arbitrary function, so the PDE should also be of first order. So we'll evaluate the first order derivatives of Z. Apply product rule to find the partial derivatives. P equal to phi of x square plus y square plus x plus y times phi dash of x square plus y square times 2x. Q equal to phi of x square plus y square plus x plus y times phi dash of x square plus y square times 2y. Now looking at the original relation, we can write phi of x square plus y square equal to z divided by x plus y. Again, substitute for phi of x square plus y square in both the partial derivatives above. Then P equal to z by x plus y plus 2x times x plus y times phi dash of x square plus y square. Q equal to z by x plus y plus 2y times x plus y times phi dash of x square plus y square. Rewrite the equations once more. P minus z divided by x plus y equals 2x times x plus y times phi dash of x square plus y square. Q minus z by x plus y equals 2y times x plus y times phi dash of x square plus y square. Now remember that we wanted to eliminate the function phi from the original relation. Both the above equations have phi dash of x square plus y square on their right hand sides. We can see that if we divide the two equations, then the phi dash term will be cancelled out. So divide the above equations, then the function phi will be eliminated and we will get an expression involving only x, y, z, p and q. P minus z by x plus y divided by q minus z by x plus y equals x by y. Now it's just a matter of simplifying this equation. P times x plus y minus z whole multiplied by y equal to q times x plus y minus z whole multiplied by x. We can rearrange this again and get the final PDE x plus y times qx minus py minus z times x minus y equal to 0. Let's look at another example of eliminating arbitrary functions. Form the PDE satisfied by z equal to f of x plus at plus g of x minus at, where a is a fixed constant. Now this relation has a fixed constant a, two independent variables x and t, and two arbitrary functions f and g. Now there are two arbitrary functions, so the PDE satisfied by this relation should have order 2. So evaluate the second order partial derivatives of z. Dou z by dou x is phi dash of x plus at plus g dash of x minus at. Dou square z by dou x square equals second derivative of f evaluated at x plus at plus the second derivative of g evaluated at x minus at. Then in the same way, evaluate the partial derivatives with respect to t. Dou z by dou t equals a times f dash of x plus at minus a times g dash of x minus at. The second order derivative dou square z by dou t square equals a square times second derivative of f evaluated at x plus at plus a square times second derivative of g evaluated at x minus at. So looking at the two second order derivatives, we can see that dou square z by dou t square is just a square times dou square z by dou x square. So dou square z by dou t square is a square times second derivative of f at x plus at plus second derivative of g evaluated at x minus at. That's just a square times dou square z by dou x square. So now we have the PDE we want. Dou square z by dou t square equals a square times dou square z by dou x square. Now in the last example, we will look at a relation where we can't evaluate the partial derivatives of z directly. Find the PDE satisfied by the relation f of x plus x square plus y square z minus xy equal to 0. The given relation has one arbitrary function, so the PDE should be of order 1. So we should get the first order partial derivatives of z. However, here we can't find the partial derivatives of z directly. So in such questions, notice that f is still a function of two variables. The first variable is x square plus y square. The second variable is z minus xy. So let u equal to x square plus y square, v equal to z minus xy, so that the relation can be written as f of u v equal to 0. Now differentiate the above relation with respect to x. Since f is a function of u and v u, v are themselves functions of z, x and y, we'll need to apply the chain rule. Dou f by dou u times dou u by dou x by dou x plus dou u by dou z by dou x plus dou f by dou v times dou v by dou x by dou x plus dou v by dou z by dou x equal to 0. Now substitute for the partial derivatives of u and v and denote dou z by dou x by p. Then we have dou f by dou u times 2x times 1 plus 0 times p plus dou f by dou v times minus u times 1 plus 1 times p equal to 0. Simply dou f by dou u times 2x plus dou f by dou v times minus u plus p equal to 0. Now repeat the above step to differentiate the relation f of u v equal to 0 with respect to y as well. Then we will get dou f by dou u times 2y plus dou f by dou v times minus x plus q equal to 0. So we have two equations involving dou f by dou u and dou f by dou v. Eliminate dou f by dou u and dou f by dou v and we'll get the required PDE. The equations are dou f by dou u times 2x plus dou f by dou v times minus y plus p equal to 0. Dou f by dou u times 2y plus dou f by dou v times minus x plus q equal to 0. Multiply the first equation by y, the second equation by x and subtract the two of them. Dou f by dou v times minus y square plus py plus x square minus qx equal to 0. That's what we get after subtracting. Now look at this expression. Basically, it says that the product of two terms, dou f by dou v and minus y square plus py plus x square minus qx is equal to 0. If the product of two terms is equal to 0, one of them should be equal to 0. Now f is an arbitrary function, so we can't really say anything about dou f by dou v. So minus y square plus py plus x square minus qx should be equal to 0. And that gives us the PDE satisfied by the relation qx minus py equals x square minus y square.